So this is the third part of the first chapter in physical science, and we're going to round it up with some general comments about the scientific method. Your book makes the point that to do science, your hypotheses, your guess of that you're going to test in the scientific method must be scientific. Since science is a trial and error testing of things, then scientific hypotheses must be testable. So what do we do today when we practice science? This diagram illustrates the process and is often called the scientific method. I'll use the example of when I went to graduate school. I chose a professor to do my research with, and he told me when I got there I had to isolate a pure biological molecule from blood that was part of the blood coagulation process. So I gathered all the information I could on how to do this, made my plans, performed all kinds of procedures on cow blood, and after 2 weeks I had a test tube with a pure molecule in it. So I had a problem, I made lots of observations, and then I had an answer to my problem. Okay. I had done it and was very proud. However, like Copernicus, my method for purification was no good unless I could test it to see if I isolated what I thought I had. So I added it to cow's blood and nothing happened. It was supposed to coagulate. So I knew my method, as great as it was incorrect. So I changed my procedures, read more on what my work, about my work, and I tried again. Made new predictions, collected more data, tried to explain my observations by trying it again. No good. Tried other things, kept revising my hypotheses about what would work, went through this cycle several different times. You can call it trial and error. Okay. And finally I reached a point where I had a test tube with something that would actually coagulate blood. So in fact, I had found an answer, and it matched what I knew I had to have. The point is that the main scientific method involves lots of trial and error until a hypothesis is shown to be correct by experiment. It is also true that you are already familiar with this method from your daily life. From my life, I have two examples. I like to cook, so some years back I decided I would like to make good bread. I got a recipe. It called for flour, eggs, milk, oil, sugar, and yeast. I put it all together and followed the directions, and when it came out of the oven, it was as hard as a rock and heavy as a brick. So I changed the amount of water and flour and butter. After several trial and error attempts, I came out with perfect, light, warm, fluffy bread. It turned out that the main issue was finding just the right cooking time. Another life example is when I first came to this school, I had to drive a lot to the other campus for meetings and things, so I asked around for what was the shortest route to the other campus. Everybody had an opinion, and I must have heard about 10 different routes. So I tried all the routes, and it turned out that the person who told me the Galva-Atkinson blacktop was right. So the scientific method is used every time we solve a problem by trial and error. Oftentimes we are informed about what to hypothesize by laws and theories. So I want you to know what these are. I have listed some laws of nature. They are statements about the way the world behaves that are essentially never violated. Gravity, that's an easy one. What goes up must come down. You all know this one. Conservation of mass, most people know about, but don't know some of the details. So you have known about it since childhood. Believe it or not, psychologists tell us that when they show a young child, maybe 4 years old, a glass of water, and then pour half of it into a second glass, the child will think you have more water after you poured it because you have two of them. But past a certain age, maybe 6 or 7, the child says you have the same amount of water. It's just split between 2 glasses. The older child understands conservation of mass. In his or her visible world, whenever things go through a process, they can change somehow, but they never disappear. As a second example, a magician on a stage opens a box, and in goes the assistant. And when he opens the box again, the assistant has disappeared, and everybody laughs. Why do they laugh? Because since they were 7 years old, they know conservation of mass. In their visible world, things just don't disappear. They know the assistant is hidden, but is there somewhere. In science class, we learn why mass is conserved. We will see later that all matter is made out of tiny microscopic particles called atoms, and that atoms can never be created or destroyed. That means that matter can change shape or color or form, but never is destroyed. Conservation of energy is another good one. We are all familiar with it. We can buy a gallon of gasoline, put it in an empty gas tank of our car, and its energy will power the car for about 20 miles. However, if we go to all the trouble to walk to a gas station, buy another gallon, walk back and put it in our car, there's no way any of us is going to drive it another 20 miles. We know that the energy in the gallon of gas will be the same as before, and it will give exactly the same amount of energy to the car because the energy is not destroyed, it is conserved. In addition to these laws, there are many, many theories. So I've just listed some examples from the first decade of the 2000s that I knew about, at least in my life. Some have a lot of evidence to support them, others not so much. What each has in common with the other is it's a simple statement that explains a lot of data. Dinosaurs. Fossils are found in several geological layers that can be dated to about 50 million years ago. But at some point there is a sharp cutoff in the fossil record indicating that they died out over a very short period of time. A very large basin is also found filled with sediment, is found under the dirt in Belize, and it is so big that it must have been made by a very large asteroid impact. The asteroid impact is dated back to the extinction date of the dinosaurs. The asteroid also left a residue of relatively rare iridium metal, and the iridium shows up all over the world in the same geological layer laid down at the extinction of the dinosaurs. Nobody knows for sure what happened to the dinosaurs because nobody was there, but all this evidence can be summarized by saying the dinosaurs were killed by an asteroid. Another example, compass needles will someday point south. We find magnetic flecks of iron laid down in the ocean floor. They align with the Earth's magnetic field when they are in molten lava, the liquid state, but when they get frozen, when it's cool, but then they get frozen there when the lava cools. And as the lava layers cool year after year, the direction of the flecks indicate the direction of the magnetic field year after year. The flecks fill over and the flecks flip over and point the opposite direction about once every 50,000 years. Nobody was around with a compass 50,000 years ago, but the evidence can be explained by a simple statement that the magnetic field did flip over and will again someday. The Y2K bug, you may remember the Y2K bug. Computer programs all had to use the current date, but the codes mainly looked for years starting with 19, that is the 1900 dates. There was a panic to reprogram everything so the world's computers would not grind to a halt at the stroke of midnight on January 1st in the year 2000. This led to lots of pretty fun New Year's Eve Y2K parties. Even though millions of dollars were eventually spent, the experts said there was no way they could have fixed all the affected programs in time. Predictions were made that banks would fail and planes would fall from the sky. But nothing happened in the year 2000. The simplest statement was that the simple statement that explains lots of evidence is the Y2K bug was a hoax. Hopefully you get the picture. The last two theories also explain a lot of information. Okay. Your book also makes the point toward the end. It's only that science has limitations. It only concerns itself with the natural world. If something is supernatural or has supernatural powers or properties, science has nothing to say about it because it's only something that can be detected, not something that's not part of our natural world. Science is also distinguished from other forms of knowledge, such as art and religion. Science involves exclusively the physical world and what can be tested about it. If compared to art, art would be the interpretation of how you might feel about the physical world, and then religion often is thought to overlap with science, but religion really is looking for meaning behind the physical world, so they can be viewed as separate entities.